Right, I'm pleased to welcome our next speaker, Osbert Bastani from the University of Pennsylvania. If you recall, in the intro talk on Monday morning, I said, one of the goals of this workshop is to bring together communities in formal methods of program synthesis and AI and machine learning and control and cyber physical systems and so forth. In fact, Osbert is all those communities in one person, right? So he's really this amazing researcher and professor who's able to straddle all of these different communities so seamlessly. And in fact, his research embodies that. So I'm really excited to hear about what he has to tell us about neurosymbolic synthesis.
Thanks for the very kind introduction. Yeah, I get stretched in lots of different directions because of my students. So I often just go kind of where they want to. And that's been a great way to learn about a lot of different topics. So today I'm going to talk about something which we've been working on for some time now. There's kind of a small community that has grown around neurosymbolic synthesis. And we'll talk about some of the work how we think about the problems related to this workshop. So just the usual motivation here is that there's a lot of systems where it's the same one I think Sanjit laid out so well on Monday, that there are a lot of systems that are using machine learning, especially deep learning. So we have this example of self-driving, where usually you have a neural network that's used for perception and sometimes for forecasting, will combine into a traditional control systems. And more recently, if you look at things like large language models, they're often incorporated. The language models by themselves can already do a lot, but if you really want to solve more sophisticated tasks, you're giving them access to tools, they're writing code. This is an example I'll come back to later, but here you're asking GPT-4 to write code that then calls vision models in order to solve some image question answering problem. So here you're asking, how should you split the muffins fairly? And it writes this Python code, which the Python code then calls an object detector in order to find the number of muffins, and it divides it by 2 to see how to split it evenly. So that's kind of a really cool example of this idea of machine learning being incorporated into a broader system. And there are some examples from our work that I just want to go through quickly to get a sense of what these programs look like. So one thing we did is neurosymbolic synthesis for web question answering. And what that means is we have you want to write a program that then traverses the AST, maybe uses word embeddings to find things like relationships. But ultimately, all of these things go into a program that outputs the answer. So here, this question is, let's extract all of the conferences that someone served on the program committee of from their website. And, the website is, people use very different formats. It's a very kind of noisy problem. So that's why you want this combination of, the neural networks to do semantic understanding with a traditional program to actually traverse the DOM. If you just use, I don't have the plots, but if you just use if you could feed, today it might actually work a lot better when we wrote this paper. If you just fed it to a language model, it might get an F1 score of 0.25. But if you synthesize a program to solve this problem, you could do much, much better. So similar story around video trajectory queries. So this is the work led by one of my students. So he's looking at, again, this kind of problem of extracting some kind of data extraction problem. So you have a bunch of trajectories that you, from a video that you extract, and then you want to look for certain behavior patterns in this data. So here we're looking at a query. So we have a query language, which kind of looks like regular expressions, but you can have predicates, and we synthesize predicates in this language. But then the predicates themselves they're related to the output of a neural network that's doing the object tracking to get these trajectories. Yeah, just quickly, I'll go through. So those are kind of data extraction problems. We've also done this for control. So you can have like neurosymbolic controllers that combine programs to kind of make high-level communication decisions with low-level control. So here's something that we did for multi-agent planning, where you have a program that kind of decides who each agent should talk to, and then you make the decisions using a neural network. And more recently, this is a pretty cool system, I think. So we have we're using a language model to do reward synthesis. So in this system, we kind of asked ChatGPT to produce a reward function. But the really interesting part of the system is it's not, zero shot. ChatGPT doesn't create a great reward function. So there's actually this loop where we actually run reinforcement learning with the reward that is synthesized. We see how well it does compared to some sparse reward. And then we try and generate better and better shaped rewards for solving the task efficiently through the iterations with, so there's like the RL simulator in the loop, there's the language model, and then there's some feedback that we get to the language model. So again, there's this system that we're building around a bunch of traditional machine learning components in order to solve a problem. And one of the highlights of this is we actually, in simulation, we were able to solve this pen spinning task, come up with a reward function that could solve this pen spinning task. So those are some examples. And again, the general paradigm I'm going to be talking about today is neurosymbolic synthesis. So in a lot of the examples I showed, not the last one, the program was handwritten, but in a lot of them, we might want to automatically synthesize the program, right? We have these custom DSLs for solving all these tasks, and ultimately, we want a user who's interested in kind of solving some problem. They're not going to be able to write programs in this DSL, so we want to synthesize a program. Most of the work I'm going to be talking about is programming by example. So the idea is that we have this DSL of programs, and the DSL includes neural network components. That's really the new thing compared to the existing programming by examples framework. And we want to synthesize a program in this DSL to satisfy user intent. And the key challenge, if we want to do this in a rigorous way, the key challenge is how do we encode user intent, or how do we, I think the user intent is usually clear, but like how do we reason about correctness of the neural network components? So I'm going to be describing two strategies that we have for handling this. One is to think about optimal synthesis. So we're going to treat this as a very similar to a traditional synthesis problem, but instead of having we just want to satisfy all the examples, we actually want to optimize some metric like accuracy or F1 score. So that's one approach. The other one, which is a little qualitatively different, is so there's a technique called conformal prediction that we've been, and a lot of other people have been working on over the last few years for quantifying the uncertainty of neural networks. So rather than treat it as a quantitative thing, we can treat it as an uncertainty quantification problem, and we'll see how we can give semantic guarantees to neural networks using conformal prediction, and then provide guarantees that way on the program that we ultimately synthesize. If there's time at the end, I want to loop back to this, this point I made that LLMs can now write the code. So coming back to this example where so in all of these examples, we have some traditional synthesizer that's generating the code, but now it seems like we've really shifted to this paradigm where LLMs are autonomously writing the code based on natural language queries. So this is really a traditional semantic parsing paradigm. But then there's a question about what kind of guarantees we can give in this space. And really the thing that one of the things I'm really excited about is whether we can come up with better programming languages. So usually these systems write Python code, but thinking about whether we can write better, have the LLM write code in better languages. Better is, in what way? So we have a couple of different features. We're proposing a new language called Quasar, and it has a couple of different features. So there's auto parallelization, so we can run these programs much faster. There's security features that we include. And we also incorporate uncertainty quantification to improve reliability. So I'll briefly touch on this at the end if there's time. But diving into the synthesis work. So I said there are these two directions. First, I'm going to talk about some of our work on optimal synthesis. So hopefully, I'm going to kind of give an overview, but there is this kind of existing synthesis paradigm where the kind of Cygus paradigm where there's this domain-specific language that's guiding the search. So you have a search space over, syntactic programs. And often naive enumerative search is very slow. So what people will do is we'll have some kind of logical reasoning, some kind of deduction to prune parts of the search space to speed up search. So if you can prove that an entire branch of your search space doesn't work, can't possibly work, then you don't need to waste time kind of traversing that search space. So how does this look like when we're looking at neurosymbolic synthesis? So we have, and so now it's the same, but now we're looking at these DSLs with neural components. And we're also thinking about how to handle quantitative objectives. And there are really two main challenges. So we're looking at, quantitative objectives I've already mentioned. So we're not going to be, I am going to be assuming the DNNs are pre-trained, but there's still often like real valued thresholds that you have to optimize. So in most traditional kind of syntax guided synthesis algorithms, you assume that the grammar is discrete, but here we have real valued parameters. So you have these kind of uncountably infinite search space in some of the productions. So just to formalize the problem, so we're assuming we're given a DSL and this encoding this program space script P, and also we know the semantics, and then we have a quantitative objective L. Oh, that's it's a loss that maps the space of programs to a real number, and we're going to assume it's minimization, and we want to find a program that minimizes the loss. So just to give an example, so it's a toy example. We'll see a more realistic example later, but here we have arithmetic programs. So this is kind of related to symbolic regression, but you can imagine a very simple DSL of just, where you have multiplication and addition of different variables. And here the loss maybe is mean squared error. So this is a regression problem. We have a bunch of input-output examples, and we want to find a program that kind of best aligns the inputs with the outputs. And if we're given 0, 1 as an input-output example, then you can kind of instantiate that. So if you have just a single example 0, 1, then maybe something like x plus 1 solves it with 0 loss. This is just for kind of, I'm going to use this as a running example. For real programs, it's going to be, this is very under constrained, but for real programs, we're not going to have that issue. So we're building on, we already saw A-star search today. So, we know how to do A-star search over program spaces, and you can apply the same thing here if you have a scoring function. So that's one of the, we'll come back to this question of what a good scoring function is. But just to recap, so in A-star search, we're basically doing an enumerative search over the space of possible programs. So if you find, the nice thing about A-star search is if you find a program that satisfies if you find a complete program, sorry, here, so P hat is going to be a partial program. So we're doing a enumerative search over a grammar. So we're going to start with, a whole that represents, we don't know anything about the program, and we're going to kind of use productions to refine the program. So this is all, that's all from traditional enumerative synthesis. So P here is a partial program. So we have this priority queue of programs according to some score. And we're going, at each step, we're going to search the program with the next score. If it's complete, we're going to return that program. Otherwise, we're going to push all the subsequent programs according to the score for each of the children. So we have a space of children here, which I'll come back to later, and then we have to push the score down. We have to compute the score of each of the children, and then we add those to the priority queue, and we kind of keep doing this until we terminate. And the main guarantee is that if the score is an invisible heuristic, which says that basically it's always an under approximation of the, it always under approximates the true loss, then this will convert to the optimal program. Okay, so this was already there in prior work. So there was some great work called NEAR that basically implements this. Sorry, before I get into NEAR, I'll say more about them in a second. But yeah, just to kind of illustrate how this works. So coming back to the running example I had earlier, where we're searching over these arithmetic expressions. So we have, we might have, we start from the whole of all programs, and then maybe we have a refinement saying, okay, this is x plus some other whole, and the score here is the same because if we have x plus a whole, well, that could still be, maybe we'll get it perfectly. We don't know. I haven't told you how we come up with these scores yet. I'll say that later. But then maybe we also have x times something, and our input-output example was 0, 1, so we know x is 0. So no matter what this is, it's actually going to, x times anything will be 0. So we know that the loss here will actually be 1. And that means that following A* search, we're going to first kind of check this branch. This branch is more promising. The score actually is just the lower bound, but I'm including upper bounds for reasons that will become clear later. But so the score here is 0, so we know that there might be something that's promising in this branch. So okay, now we might fill this in with 2. Well, that wasn't a great choice because then we get 2 instead of 1. If we do x plus 1, this program solves the problem. So that gets us the score of 0, 0. So yeah, I should have mentioned this, but yeah. So here the score is not, earlier I talked about the score as a real number. Here it's an interval, but the score that we get is actually the lower bound of this interval. Yeah. So this is the basic intuition behind how A* search works, if you have a scoring function. Okay. Okay, so we need a scoring function. That's the first challenge. So this previous system I mentioned, NEAR, uses A* search, but they use it with a neural network to approximate the scoring function. And it's a very clever strategy. I'm not going to go into it, but if neural networks are kind of can learn any function, then this will work, but they can't. So in practice, it's not guaranteed to satisfy the condition. The other challenge is how to search over real valued parameters. NEAR kind of solves this by just doing gradient descent, but gradient descent is incomplete. So if we really want optimality, we're searching over these uncountably infinitely large sets of these thresholds. Like in this previous example, what do we fill in this hole with? It's not, we can't really enumerate all possibilities. So enumerative search breaks down. Okay, so those are the two challenges. How do we address them? So I'll just go through them one by one. So the first one we address by using abstract interpretation. So how does that work? What we're going to do is we're going to fill all the holes with the abstract value top. So we don't know what the value of the hole is. So we're just going to fill it with anything. And then we're going to basically propagate these scores, these abstract values through the program. And it's pretty easy to show that. So for example, you could use interval semantics in the arithmetic domain. I'll go through that example in a second. But you get some abstract value for your loss function. So you need an abstract semantics for your programs. You need an abstract transformer for your loss function. But if you have that, then you can guarantee that with this strategy, for any completion, because we've kind of filled all these holes with top, for any completion of our current partial program, the loss of that program is going to be contained in the interval. So this motivates what I showed earlier, which is that, so we get an interval for our score, and we can guarantee that for any child in our search tree, it's going to be contained in that interval, and therefore a valid scoring function. We need a lower bound, so a lower bound on L of P for any completion of P hat is just a lower bound on the abstract value. So we can use, for example, the infimum. If it's an interval, it's just the lower bound of the interval. So just to walk through an example, this was the example I showed earlier, where we knew that 0 times anything was could only be 0. So here the loss is 0 times the program is this, and the loss is the mean squared error. So we're going to substitute the hole with top. For interval semantics, we're going to substitute it with minus infinity to infinity because it can be anything. And then we use abstract interpretation to propagate. So when we multiply this by 0, we get 0. That was the main insight. And then we subtract 1, we get, we know that the loss has to be 1. And then when we score it, it's still 1. So we get this interval. In this case, it's really just a single value because we know that no matter what we put for this hole, the loss has to be 1. So that's how that works. And so we can conclude that. And if you take the infimum, you get 1. So that's where the score comes from. Okay, so this is the idea. So we can use abstract interpretation to get a valid scoring function. So that's the kind of first key insight. The second one was this question of using children. Sorry, how do you do search over these kind of infinite grammars? And the idea is that rather than, so in enumerative synthesis, you often assume that you're just enumerating terms according to productions in your grammar. But what we're going to do is we're actually going to allow the enumerator to basically decompose holes in other ways. So we introduce this idea that holes can be kind of labeled with constraints. And what a hole with this label C means, so C here is some kind of a constraint. We'll see an example later. But it means that the hole can only be filled with an expression that satisfies this constraint C. So one caveat here, in traditional syntax-guided synthesis, you just, as a user, you just provide the grammar and that specifies the search order. But here you actually have to provide, exactly how the children are completed. And so it's a little bit more work for the user to do, but we'll see that you get some benefits out of doing this. So the main,
Osbert, can you elaborate exactly what that means? So when you say the user must provide the children, I didn't fully understand how that is specified, how this is provided.
So we'll see an example, which I hope will make it more clear. I mean, basically, you have to, like if you wanted to recover traditional syntax-guided synthesis, you would just enumerate through all productions and use them to fill it in, and that would be your set of children, right? But here, there are different...
you mean just generate full expressions as opposed to the grammar? Like,
I think it'll become more clear.
Okay.
Let me give an example on the next slide. But yeah, the condition is that if I have a child, this should be p hat here, but if whatever function you give me, the children function, if I have a child, then the completions of that child, here completions are all possible programs that can kind of be obtained from a partial program. So the completions of p hat prime are a subset of the completions of p hat. So both of these should be hatted here. Okay, but yeah, an example I think will help. So in our grammar, we can have holes that have these real valued constraints. So this says two things. So a hole, I guess usually a hole is also labeled with a non-terminal, which I've elided. But if you have a hole that corresponds to a real number, normally that means that that hole can be filled by any real number. But we're going to consider holes that have these restrictions that say that this isn't any real number, it's a real number between A and B. So this lets you, and maybe when you provide children, there are various ways you can construct the children function. The simplest one is to just do bisection. So you can introduce a hole like this by saying that a hole, the child of any question mark could be a question mark with minus infinity to infinity, and then you can refine that hole by basically bisecting. So when we have AB, we'll only, rather than considering all possible children of filling this hole with some real number between A and B, we're going to split this into two subintervals here. So there is a question this raises about the completeness of the search, which I will touch on later. But yeah, yeah, just stay tuned for that. Okay, so just to kind of continue this example, so how do we actually do search now? So we had this branch where we had x plus question mark gets mapped to this 0 to infinity. So now that comes from abstract interpretation. And then now, I skipped a step in this example. So this hole, this should be labeled with a constraint from minus infinity to infinity to say that it's some real number. And then we might consider a child where you have x plus question mark, and then the question mark is labeled with 2, 4. And in this case, you would know that the score is 1, so yeah, one thing that changes now when we do abstract interpretation is we don't the top basically for this is really the interval 2, 4 instead of minus infinity, infinity. And we might also have a child that's 0, 2. And there maybe we'll also have additional children. We might have minus infinity to 0. We might have 4 to infinity as other children here. But for this value, if you plug it in, you know that the score is between 0 and 1. As before, so A star search will kind of pick the most optimistic branch to kind of continue searching. So this branch is, the lower bound is 0. This branch is the lower bound is 1. So we'll kind of optimistically continue down this branch. Okay, so yeah, there are a couple of things I've swept under the rug here. But this is the kind of general idea. So yeah, I mentioned completeness. I want to loop back to that question. So because of the way we've structured the search space, we never actually, it may be that we never converge, right? Because we could just keep expanding and refining and refining. What happens though in practice is that at some point you refine this interval to something small enough and you actually find that the score is the same here. So we actually get a space of possible real valued parameters, all of which map to the minimum score. And then that's when you can stop. So you can stop once you have a partial program such that everything in that interval is guaranteed to map to the same minimum score in A star search. So it's not guaranteed to happen. If you're worried about it for some DSLs, if you're worried about it, you might set an epsilon threshold for stopping. So once this interval is smaller than epsilon, then you stop. And then you can pick any program by choosing some value in that set, and then you'll get something that's within epsilon of optimal. Okay, so I'm gonna go through the application. So we have this application to video trajectory queries. I'll go through the DSL is pretty standard. It's really a Kleene star algebra with tests, but where the predicate, so it's like, you can think of it as regular expressions, but where the predicate, where instead of characters you have, or symbols, you have predicates, and then those predicates can be conjunctions and disjunctions, and ultimately the base predicates can either be traditional like symbolic ones or these neural predicates. The neural predicates here, theta is a real number that says the threshold on a neural network. So you're going to output true if the neural network predicts a probability greater than some value. You're going to output false otherwise. So those are the real numbers that we have to search over. So some examples of predicates are: is the car in a certain lane? Is car A in a certain lane? What's the displacement from the sorry, I actually don't remember what that one is, but you also have like the speed. So this is another one where you have a real valued predicate, but you can imagine, is the car's speed bigger than or equal to some threshold? Or bigger than some threshold. That's another, yeah. What's the U operator?
The U operator, the
that's
Q,
a good question.
Q, U.
I believe it's is it until
I mean, is this a formula? Is it a Q basically? It's not. It's got semicolon, right? So it's like I don't know what's the type of
this
Q.
Is so you have sequential conjunction, you have Kleene star, and
Sorry, non-deterministic.
I don't remember.
Okay.
I'm sorry. It's it's been a while since.
But just broadly, like, what is Q? Is it like a statement, or
Q
is it
the query.
Formulas?
So that's
query.
the full,
I see.
yeah. So like this is an example of.
Oh, I see. Sorry, I missed this.
Yeah.
So it's
actually I have two
query
more,
over basically sequences then.
Yeah, and you can. It's actually
right.
a little richer than what I said. The Kleene algebra with tests. So you can have like. So one thing you can do is you can have conjunctions, but you can also, have conjunctions with some star outside of it and things like that. So it's a little richer than your usual regular expression language, but really it's most of the queries look something like regular expression. So here, yeah, I don't want to go into too much, but here this says that it's there's some point in time at which the car is in lane 1 and it's not moving within below some threshold. So there's noise. That's why you need a threshold here instead of not moving at all. But if you're stopped, then if you're moving very little, then that means you're stopped. And then this one is a more complicated query that says you kind of, I believe this one says you overtake someone and then you change lanes into them. So you were previously behind, like previously A was in front of B was in lane 1, and then, this might be, yeah, but there's something where, B is changing lanes into the same lane as A. Yeah. But just kind of going very quickly through the results. So yeah, we have a setup where we run the object tracker on a video to get trajectories, and then there are these domain-specific features, and then we also have an active learning loop. So since I'm not going to go, it's a pretty standard thing where you basically use the best, you choose the example to label that best splits the search space. But yeah, there are some connections to machine teaching, which we saw today morning, but we're doing very basic stuff here, so nothing too fancy. But we actually find that active learning is really effective here. So machine teaching works in some of these practical settings. But here we plot after, it's a little hard to see because, yeah, we bolded the best, but basically the takeaway is that Q is our approach. So after 25 steps, I think we solved 15 out of 17 of the benchmarks with near perfect accuracy, whereas the LSTM is L, and logistic regression is another one. So these benchmarks both do a lot worse. So deep learning here logistic regression is a transfer learn. So LSTM is just trying to train an LSTM on 25 examples. So it's not too surprising that didn't work. But we also tried a transfer learning strategy where we pre-train an LSTM and then just run a logistic regression on top of that. That works a lot better, but we still beat it in most of the cases. And we also compared, this is to meta sketches. Meta sketches is, it's not surprising that I think we do so much better, but meta sketches is an SMT solver-based approach for solving the optimal synthesis problem. But they target a very different domain. So it's not really good at handling these real valued parameters. And that's what we kind of see is that we're 2 orders of magnitude faster than meta sketches. Yeah, so I guess the 2 takeaways. So using abstract interpretation, we can do this kind of deduction guided search in the neurosymbolic setting. And one of the interesting things is we did have to, unlike traditional syntax guided synthesis, I think we need a richer way of specifying how we search over programs in this setting to handle these kind of continuous parameters. Okay, any questions about this before?
Yeah, I have a question here. So you have it. So very interesting. So my question is like, it seems like there's some other things that's under the rug. In particular, you are like the examples you gave heavily utilizes intervals. Now, I was wondering for more general loss functions, that's not square loss. Like, let me construct a crazy one, right? So your function, function x minus y, the value. Let's just say the loss is 1 if it's rational, and 0 if it's irrational, and so on. But that certainly would not decrease your as you go down the branches, right? So my bigger question is like, is this so that this is a conscious choice on your side, and it somehow works really well with the type of neural networks that we're currently seeing, so that it is doing something really efficient?
Yeah. So first of all, just to be clear, we're not using this to train the neural networks. So the neural networks are pre-trained. We're only using this to tune the thresholds. So it's really more a question of your language of programs. And yes, this worked really well for the languages that we considered, but you're absolutely right. You can come up with examples, even realistic examples, I think, where this doesn't work very well. So that's, I think the nice thing about abstract interpretation is it is a general framework. So if you have, domain-specific insights, you can design abstract domains that are suited to reasoning about programs in your DSL. So, yeah.
All right, thanks.
Okay, so I think I'm a little short on time, so I'm going to go through this second part a little quickly. But so that was the first piece where we're trying to do optimal synthesis, and then there's this alternative approach I mentioned where we're trying to instead of thinking about it as, let's say we do want semantic guarantees for our programs. We're not satisfied with just kind of getting good accuracy or F1 score. What can we do then? And the challenge here, of course, is that we can never guarantee that the neural network gives you the right answer. But we can maybe ask for the neural network to say when it doesn't know. And we're going to use conformal prediction here to kind of as an uncertainty quantification strategy. I think it's nice because it gives you these kind of theoretical guarantees without theoretical guarantees that kind of make intuitive sense and work well with programs and symbolic reasoning. So for just to give very quick background on conformal prediction, the idea is that you have a traditional neural network, which say ImageNet, it takes an image and it makes a prediction. Sometimes it gets it wrong. In this case, it's actually interesting because it's actually not clear what the ground truth label is, right? Like it could actually be multiple different things. And the idea in conformal prediction is to replace this neural network with modify it to output sets of labels. I'm not going to go there. There's a whole theory about how to construct these sets. I'm not going to go into that. The only kind of important bit is that we're going to modify our models to construct sets of outputs. And the nice guarantee I mentioned is that these sets contain the true label with high probability. So that's conformal prediction in 1 minute. So here are some examples on ImageNet. You can see, it outputs these labels. And I think the prediction sets kind of scale nicely with the intrinsic uncertainty of the image. And we can also do it for things like object detection, where we have a bounding box that kind of over approximates the true bounding box. Oh, yes.
So do the labels also come with some kind of confidence or something?
No. So in conformal prediction, you usually it's a different approach to quantifying uncertainty. I mean, you can still look at the confidences from the original neural network, but it doesn't try to adjust the confidences in any way. It's purely this kind of set-based quantification of uncertainty.
So all of them are to be treated equally?
Yeah. But I think it's nice because reasoning about probabilities is hard. Reasoning about sets we know how to do, and we'll see a little bit of that soon. Okay, so what does this have to do with programs? Well, if we have a neurosymbolic program that's kind of has some neural networks in the loop. So here, this is a simple example. What this program is doing is we take as input this a list of digits represented as images and another digit represented as an image. And it basically wants to filter everything that's kind of bigger than or equal to, filter everything in this list that's bigger than or equal to this number. Okay, so here we see we're going to first predict that that's 2 using a neural network. We're going to predict that this is 0, 4, and 5. And then when we execute the filter, we just get 4 and 5 left. Okay, so a very simple program. And but what if the neural network makes a mistake? So instead of 5, it mispredicts this as being a 3. Then we're going to get the wrong output, obviously, right? So what are we going to do with this? Well, I already gave you the answer. We're going to use conformal prediction. So instead of filling these things in with just a single prediction, we're going to get sets of predictions, right? So here, and I'm ignoring even the conformal predictor has a high probability guarantee, but if we sweep that under the rug, we're guaranteed to have the true label somewhere in this set. And then we can use, say, set semantics to propagate this prediction sets through, and we get these, so now it's either 4, 3 or 4, 5. And the ground truth we know is 4, 5, but it's in the output of the program somewhere. So here I said we could use set semantics. We can also use abstract interpretation to propagate prediction sets through the program, and that'll become important later. But now I want to come back to program synthesis, right? So I started off saying, okay, so we want to use this to do synthesis. In traditional synthesis, you want to get the answer exactly right. We saw kind of an optimal version of synthesis, but here we're going to modify it. So we still have a semantic guarantee. What we're going to guarantee is that the true label is in the prediction set of the program output. So what we want to say is, if a program kind of plausibly is consistent with the true label, then we'll keep that program, right? And this is a semantic guarantee because, if we do have the true program and we run it with conformal prediction, well, maybe we don't know what the ground truth label is, but we know it is somewhere in that set, and then you can kind of act in a way that's conservative with respect to the uncertainty. Okay, so, so here, note that, because we want to be as precise as possible, here I'm using the set semantics. So that's going to come back. I'll mention that again in a second. But the basic algorithm is we could actually just run enumerative synthesis with this logical specification, and we'll get some program out at the end. So there are kind of two issues. The first issue is running the set semantics is really slow, or can be very slow. And I already mentioned we could use abstract interpretation to propagate. You can change all of these sets into intervals and propagate them through the program. But obviously that's going to be imprecise. So we have this key insight that we actually don't, for synthesis, we actually don't care about computing the set of all. We only care about answering these queries about whether the true label is in the prediction set, right? So what can we do with that? Well, what we can do is we can first evaluate the conformal semantics. If we find that Y is not in the prediction set, then we know that by the conformal guarantee that Y is not in the, by the abstract interpretation guarantee, it's a sound over approximation, so we know that Y is not in the set semantics either. So if we find that it's inconsistent, then it's definitely inconsistent. The converse is a little trickier, but what we can do is we can do a kind of a backwards refinement to try and find concrete values for the neural network components. In the interest of time, I'm going to actually, so this lets us say that if we find that, this lets us say, Y is affirmatively in the set semantics. And we only need to kind of run this more expensive set semantics if both of these fail. And in the interest of time, I have this example here. I'm happy to go through it offline that kind of explains how we do the backward refinement in the second step. But I'm going to skip it. But yeah, so we have that strategy. The other thing we do is we also do active learning. So again, machine teaching works. It's pretty standard, so I'm not going to go through it. But basically, if you've seen active learning for traditional program synthesis, we have a very similar algorithm, and you basically look at the pruning power. So what you choose the example that is guaranteed to prune the most programs in the worst case over the user responses. So in the traditional literature, usually you use the expected pruning power. Here we're looking at the worst case pruning power over user responses, and that just works better with conformal prediction. But otherwise, it's exactly the same. And we have some optimizations here that show that to get a speed up compared to, so I'm not going to go through the results. Basically, our system works. You get the right, we solve the benchmarks most of the time, so conformal prediction works. And we also have a bunch of optimizations that and our question selection kind of does really well compared to some kind of existing and naive baselines. So yeah, that's just to summarize. So we showed that conformal prediction lets you get these semantic guarantees for neurosymbolic programs, which we can then leverage to solve the synthesis problem. So yeah, I didn't get to talk about this last piece, but it is something I'm really excited about. So if you're interested in basically how we can build better programming languages for LLMs, I'd be happy to talk to you about it offline. Thanks, and I am happy to take any remaining questions.
Any more questions?
So you can, right? So you use conformal prediction to give probabilistic guarantees, right? Because you were looking at a single decision and you could get that.
Yeah.
But if you collected a series of decisions, right?
Yeah.
And then you had the way that the different predictions were agreeing and disagreeing, you could turn that into logical guarantees because you could figure out the set of all possible.
Yeah, it depends on what exactly. So that's a great question. So everything I talked about is assuming that the conformal sets are correct, then you do get the logical guarantee that your synthesis algorithm is correct. But like you said, ultimately conformal prediction is a high probability guarantee. I swept that under the rug, but if you want to be, there are two separate things that you can do. In our application, because if you have one model and you're applying that model separately in multiple places, if you want to get the probability guarantee, you have to actually be conservative with respect to all the errors. So you need to take a union bound. So you kind of get, if you have like your conformal guarantee gives you coverage of 1 minus epsilon, then you get 1 minus k epsilon, where k is the number of uses. There's a different thing you can do where if you have independent experts, then you can do an intersection because you know that the conformal guarantee is true for each one separately. And then that lets you take an intersection of the prediction sets. But that's, which is something that can help. And we use something along those lines.
What I'm saying is that when you look at collections of decisions, right, then we can disregard completely the issue of whether they're error independent or whatever, right? We can just go through that logical enumeration of all the possible ways that they could have be correct, right? And then we know.
Right. So my point is that for ours, you would end up with basically the same thing in all the prediction sets. But if you do have experts that are like, I mean, there's no assumption, right? But if you have experts that are making decisions on basis of different information, then their prediction sets might overlap in ways that taking the intersection is useful. Yeah, but it's not going to help in our setting. Yeah, that's all.
Right, let's thank Osbert once again.
Thank you.
Okay, and we'll break for lunch and reconvene at 2 p.m. What is the